Linear ionic crystals. Consider a line of two capital N ions of alternating charge plus or minus Q with a repulsive potential energy capital A divided by capital R to the power N between nearest neighbors. Part A, show that at the equilibrium separation in CGS units, the potential energy evaluated at the equilibrium separation capital R sub 0 is equal to minus 2 capital N Q square natural logarithm 2 divided by R0 parentheses 1 minus 1 over N. To obtain the results in SI, we replace Q square by Q square over 4 pi epsilon 0. Note, we should not expect to obtain this result from the expression for U of R0, but we must use the complete expression for U of R. So that's referring to part B of the problem, so we will worry about that later. Okay, so we have a one-dimensional chain of two capital N ions. So here is the ith ion, and it has on its right side the ion number 1, then ion number 2, ion number 3, alternating charges, and we have a symmetric situation on the left side, 1 prime, 2 prime, etc. So capital R is the nearest neighbor distance, the distance between two nearest neighbor ions. Okay, now what is the potential, pair potential for this? In between the ith and the jth ion, we have the Coulomb interaction. So we have plus or minus Q squared divided by Rij. Now, why do I say Rij? It's the distance between the ith ion and the jth ion. For example, for this reference ion, ith ion here, and the ion labeled number 3, it will be 1, 2, 3, 3 capital R. Okay? And this pair potential is such that for like charges, that is to say, if we have plus plus or minus minus, we're going to have a positive potential that is going to be repulsive. For opposite signs of charges, for plus minus, for example, this pair potential will be negative, so it's going to be attractive. Then we can write the sum over J not equal to I for the ith reference ion, the total pair potential Uij as so between the ith ion and the first ion, we have an attractive potential. So it's going to be minus Q squared divided by Ri1. Between the ith ion and the second ion, we have a positive potential plus, because it's the charges are like, so they're both positive, Q square over Ri2. And then for the third one, it's going to be minus, it will be attractive, minus Q squared over Ri3. And for the fourth one, it will be repulsive again, plus Q squared over Ri4, etc. So this will continue like this. Okay, so for the first one, it's plus minus negative, second one plus plus positive, negative and positive. So that's what I have here, negative, positive, negative, positive. Okay, if I write the total interactions, so the total interactions involving the ith ion is going to include this pair potential. U sub I is basically sum over I not equals to j or sum over j. Let me do this summation over j. Sum over j not equal to I, uij, this pair potential, and then we have the nearest neighbor repulsive term plus capital A divided by capital R to the power n. So this is what was suggested in the problem statement. We have a repulsive potential energy between nearest neighbors. So we only consider the nearest neighbors for the repulsive one. The repulsive potential energy between next nearest neighbors is negligible. Then we have this Coulomb energy for alternating ions. So that's the that accounts for the total interactions involving the ith ion. All right. So we can write this as U sub I is equal to sum over j not equal to I plus or minus q square over rij. So that's basically this term here, plus the repulsive term, that's due to the nearest neighbor. And we can see that this can be written as q square times sum over j not equal to I plus minus divided by rij. Okay, so what is this sum over j plus minus divided by rij? That's what we need to look at now. Sum over j not equal to I. We have plus minus divided by rij, distance between ith and jth ions. It's going to be, for the first term, it is this distance between the ith and the first ion is capital R. So the first term is minus 1 over R. So first we have minus 1 over R. Then we have for the second ion, the distance is 2R and it's positive, so it's plus 1 over 2R plus 1 over 2 capital R. For the third one, it is 3R now, and it is negative because it's an attractive potential, minus 1 over 3R minus 1 over 3 capital R, and for the fourth one it's positive again, plus 1 over 3R plus 1 over 4R because the distance is now 4R, etc. So this continues like that. And this result that we obtain by looking at j equals 1, j equals 2, j equals 3, etc., we have the symmetric situation on the left side. So we also have to account for interactions with these ions. So because it's completely symmetric situation, we have to multiply it by 2. All right. So basically the factor of 2 accounts for right and left neighboring ions. All right. Now, what is this summation? So that's what we're going to try to understand. So if you consider natural logarithm of 1 plus x, the Taylor series expansion for x around 0, so x is close to 0. This is going to be first term. We evaluated at x equals 0. We obtain natural logarithm 1. Then we have to take a derivative with respect to x. We obtain plus 1 over 1 plus x evaluated at x equals to 0 multiplied with x. Then we take a second derivative, which gives us minus 1 over 1 plus x squared, but we have a 1 over 2 factorial now. 1 over 2 factorial. 1 over 1 plus x parentheses square evaluated at x equals 0 multiplied with x squared, which it's actually x minus 0 parentheses square, which is x squared. Then we take another derivative. We're going to get from here a factor of 2 from the derivative of 1 plus x to the power minus 2. So we will get a minus 2. This will make this minus sign plus. So this will become plus 1 over 3 factorial. 1 over 3 factorial. 2 over 1 plus x cube evaluated at x equals to 0, x cube, etc. So that's the Taylor series expansion. Now what is this equal to? You can see that this is the first term, this is 0. Here this is going to give us a 1 times x, so we obtain x. And then the second term, evaluate at 0, this is 1. 1 over 2 factorial x squared, so minus x squared over 2. So we obtain minus x squared over 2. And then here we obtain x equals to 0. This is 2 over 3 factorial. The 3 factorial is 3 times 2, so we will obtain 1 over 3 here. So plus x cubed over 3. X cubed over 3. And then we will obtain minus x to 4 over 4, etc. So higher order terms. Or we can write the Taylor series approximation for natural logarithm of 1 plus x for low values of x is close to 0, as sum over n equals 1 to infinity minus 1 to the power n minus 1 x to the n divided by n. So let's check. If n is equal to 1, I obtain minus 1 to the power 0, which is 1, x to 1 over 1, that's the first term. N equals 2, minus 1 to the power 2 minus 1, so I will obtain a minus sign, x squared over 2. N is equal to 3, that's this term. 3 minus 1, 2 minus 1 squared will give me a plus. X cube divided by 3, etc. So this really generates for us this series expansion. Now, when we say x is equal to 0 or x is close to 0, how close should it get? Well, let's take a look at this function, natural logarithm of 1 plus x. So this is plotted y equals natural logarithm of 1 plus x, y of x as a function of x. That's this red plot here, you can see. If I plot these four terms, x minus x squared over 2 plus x cubed over 3 minus x to 4 over 4, that is this purple curve. Now you can see that at x is equal to 1, still this approximation is quite good. So x equals 1 is close enough to x equals 0 to have a good match between the Taylor series and the actual function. Okay, so that I see from the plot. So that means I can easily set x is equal to 1, and that's close enough to x equals 0 for this approximation to hold, so that my summation over j not equal to I plus or minus divided by Rij. This term is, as you can see here, minus 2 over capital R. Then I have the first term is 1. The second term is minus 1 over 2. The third term is plus 1 over 3. The fourth term is minus 1 over 4, etc. And I can recognize what I have here as approximately being equal to minus 2 times natural logarithm 1 plus 1. So I evaluate natural logarithm 1 plus x at 1. And that basically gives me this approximation divided by capital R. So I can see that this is minus 2 natural logarithm 2 divided by capital R. Okay, so that's the mathematical trick we have to play here in order to see what approximates this series nicely. So that's basically natural logarithm of 1 plus x evaluated at x equals to 1. The Taylor series expansion around x equals to 0 gives a nice approximation for the value of the function at x equals 1. Okay, so let's use this result. Going back to our general expression, we have Rij, the distance between the ith and jth ion, written in terms of the nearest neighbor distance, capital R. So sum over j not equal to I. Instead of plus or minus, if I use minus or plus Rij divided by Rij, this is sum over j not equal to I minus or plus Pij capital R. This is equal to, now you can see plus minus divided by Rij was minus 2 natural logarithm 2 over R. Minus plus is plus 2 natural logarithm 2 plus 2 natural logarithm 2 over R for a one-dimensional chain. So this implies that, so for 2 capital N ions, we can write the potential energy U as a function of R, capital N times the repulsive potential A divided by R to the power N, and attractive potential minus alpha Q squared capital divided by capital R. Here we recognize alpha, the Madelung constant, to be 2 natural logarithm of 2. All right, so basically we have evaluated the Madelung constant. So now you can see, because I write the potential this way as the explicitly as the repulsive term, positive term, and negative attractive term, in the original potential this was written as both terms were plus, so I have to basically go from plus minus Rij to minus plus Rij in order to get this minus sign in action. And that's why my Madelung constant becomes plus 2 natural logarithm 2, not minus 2 natural logarithm 2. Okay, so Madelung constant alpha here is basically sum over j not equal to I minus plus divided by Pij, and that is equal to plus 2 natural logarithm 2. Now, if I look at this situation at equilibrium, having found this potential, I can see the nearest neighbor, equilibrium nearest neighbor distance by taking the derivative of the potential del U del R, evaluating it at the equilibrium separation between nearest neighbors R0. This is going to be the derivative with respect to capital R del R of capital N number of ions divided by 2. Basically, we have, because 2 capital N ions, a r to the power minus n, and then we have minus alpha q square r to the power minus 1. So we need to take the derivative of this and evaluate it at the equilibrium separation R0. And this is going to be equal to capital N times, now this derivative will give me a minus n here. So minus n capital A R0 to the power minus n minus 1. And then this derivative will give me a minus 1. So I will have plus alpha q square R0 to the power minus 2. And this is equal to 0 at equilibrium. Okay, so if I rewrite this parenthesis, set it equal to 0, I find that I have minus n capital A divided by R0 to the power n plus 1. And then I have plus alpha q squared divided by R0 squared. Now what I'm going to do is basically, let me go to blue here. I'm going to take this and multiply it by R0 square. And remember, this is equal to 0. So I multiply both sides by R0 square. So I will find minus NA R0 squared divided by R0 to the power n plus 1 is equal to minus alpha q squared. The minus signs will become plus, and I will find that R0 to the power n plus 1 is equal to NA R0 square divided by alpha q square. Now what I need in this expression is R0 to the power n. So I take this into R0 parentheses. So I will find that I have R0 times R0 to the power n. So this is basically R0 to n plus 1. Minus NA R0 divided by alpha q square. This is equal to 0. So now I can see what R0 to the power n is. All right. So R0 to the power n, R0 to the power n is NA R0 divided by alpha q square. Okay, so this is the equilibrium separation R0, and I will evaluate the potential energy. So the question was, at equilibrium separation, this is the potential energy, U of R0. So I will evaluate it at this value of R0. U evaluated at R0 is capital N, A divided by R0 to the power n, which is A divided by NAR0 multiplied by alpha q squared. This is nothing but A divided by R0 to the power n. That is this first term here. And then I have minus alpha q squared, Madelung constant, q squared over R0. And this gives me, for the potential energy, let's see here, we have a cancellation of A's. U of R0 is equal to minus capital N alpha q squared divided by R0 parentheses divided by R0. I will obtain a the first term I will obtain is n alpha q squared over R0 minus, so that's basically making this part plus, and then I have minus 1 over n. Okay, so this term minus minus becomes plus, n alpha q squared over nr0, that's going to be this term. And alpha is equal to 2 log 2. So I know that alpha is equal to 2 natural logarithm of 2. So my final answer for the potential energy evaluated at the equilibrium separation R0 is going to be, let's see, when I substitute the value for alpha 2 log 2, it's going to be minus 2n alpha q squared natural logarithm 2 divided by R0 1 minus 1 over n. And this is in CGS. Remember that in order to convert to SI, all I have to do is replace q squared. Q squared goes to Coulomb's constant times q squared, 1 over 4 pi epsilon 0 q squared, to do the calculation in SI. Now let's check if this answer matches the suggested answer in the problem statement. Minus 2 capital N q squared natural log 2 divided by R0, 1 minus 1 over n. So it indeed does. Okay, so we considered a line of two capital N ions of alternating charge with a repulsive potential energy A divided by R to the power n only between nearest neighbors. So first we have written the pair potential for the ith ion. It consists of plus minus q squared over Rij, which has terms as minus q squared over Ri1 plus q squared over Ri2, etc. It's minus for attractive, plus for repulsive terms. And the total interactions is sum over J of this pair potential plus the repulsive term, capital A divided by R to the power n, the Pauli exclusion term. And when we have written explicitly this pair potential summation, we realize that we have to multiply it by 2 because we have contributions both from the right hand side and from the left hand side. And we have recognized what we have in the parentheses here as natural logarithm of 2. So this is basically natural logarithm of 2. How did we see that? We looked at the function natural logarithm of 1 plus x, Taylor series expansion about x equals 0. We have seen from the plot of this function that the Taylor series expansion about x equals 0 well approximates the function even for x equals 1. So if I substitute x equals 1 here, in the minus 2 over r parentheses, what I have here is basically 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. That's natural logarithm to approximation. Okay, so this allowed us to recognize the Madelung constant to be 2 log 2 when we have written this as minus plus divided by Rij instead of plus minus, because the way we write this Coulomb potential, the total potential as capital N A divided by R to the power N, the repulsive term minus alpha q square over R attractive term. So because of this minus sign here, this plus minus turns into minus plus and Madelung constant becomes 2 log 2. So substituting that for alpha in our final expression, we will get the answer. So we take this expression, take its derivative at the equilibrium separation, set it equal to 0. We find that R0 to the power n is NA R0 over alpha q square. When substituted here, you evaluate that R0, A divided by R0 to the power n minus alpha q square over R0, where R0 to the power n is this. We obtain this final answer when we substitute for alpha 2 log 2. And this is in CGS units. To convert the SI units, q square will be replaced with 1 over 4 pi epsilon 0 q squared.